Yep, great.
Okay, thank you, Andrew, for the introduction. And I would like to thank the organizers for inviting me for this wonderful talk. So I will today try to tell you a little bit about our recent experiments on the thermalization dynamics on our Bose Hubbard quantum simulator. And in particular, we will talk about two experiments, one on the thermalization dynamics of a lattice gauge theory, while the other is on the quantum many-body scarring in the Bose Hubbard system. So, well, the question that we are interested in is this isolated quantum many-body system, which evolves under the unitary evolution. And although the whole system remains a pure state during the evolution, the whole local observables usually develop a thermodynamic description, and which can be described by this eigenstate thermalization hypothesis, which postulates the eigenstate in the middle of the energy spectrum are just random vectors, which are thermal. So for ergodic system where you have the energy repulsion, as the system evolves, the dephasing just takes you away from the pure, well, to the thermal equilibrium. And this is demonstrated beautifully in this paper in the Graner lab, where they find this thermalizing system where it establishes correspondence between the local density matrix and the thermal density matrix, with the quantum expectation value of a system will be equivalent of the thermal ensemble expectation value. And also the quantum entanglement entropy will be corresponding to the thermal entropy. So as you can see here, the statistical mechanics description would emerge out of quantum dynamics. Now, how about a system that's constrained by gauge symmetries? So basically, what happens if we have quantum field theories? Now, why do we want to study gauge theories? Well, let me quote this ancient book that says, well, in the beginning was the word, and let's give that word a little bit content. It says, well, indeed, the gauge theories offer a fundamental description for the elementary particles that make up the everything in our universe. And in fact, this is the story of creation, since our early universe is filled with all these elementary particles. And as they glide and relax, till today, we can still see this afterglow of the genesis, which is the cosmic microwave background. And if we look at it closely, it's surprising that this thing is homogeneous almost everywhere with the same temperature. So it indicates that this far from equilibrium initial state, as the early universe is, and of this isolated quantum many-body system, which is constrained by gauge symmetry, could eventually relax to thermal equilibrium through unitary dynamics. And this is where our story of quantum thermalization comes in. And I would like to show you that this will be possible just through unitary dynamics. Now, of course, there is high-energy approach toward this problem, which is by doing the particle collision to mimic the condition of the early universe. And excuse me. So, and we can detect what's kind of coming out of this collision, but it's not possible to look at the relaxation process real time. So, of course, one could also try to numerically simulate the problem, but usually if you simulate quantum many-body problem with classical computers, you often run into the sign problem, which eventually, even with the most powerful supercomputer, the things that we can calculate is still very limited. Now, in recent years, we developed these synthetic quantum devices that can help us solve quantum many-body problems with quantum many-body systems themselves. In fact, there are plenty of works in the past recent years from the cold atom community to solve the gauge theory problem, and I list a few here. But I want to highlight that it was our group that 2 years ago made this advance to go beyond single body physics, to go beyond the building block physics, and actually observe gauge invariance in this large scale Bose Hubbard quantum simulator. So this time we will be building on that experiment and go beyond equilibrium physics. So we'll be studying the far from equilibrium relaxation of a gauge theory. Now let me tell you briefly about how our experiment looks like. Well, it's a optical lattice system with rubidium-87 atoms, which is a boson. And we can have this three-dimensional optical lattice. And we first cool the atoms to the Bose-Einstein condensate and load them into a single light sheet, as you can see here, and then perform this superfluid multi-insulator phase transition to load the atoms into a two-dimensional optical lattice. And those atoms will be used as qubits for quantum simulator. And a key feature of our system is this spin-dependent optical superlattice, which consists of these two lasers that with twice the frequency of another. And you can tune the phase between these lasers to form double well potential or the staggered potential as you want. And further, we can tune the polarization of the blue lattice laser and create this spin-dependent effect in the optical lattice, such that the left sides of the double wells will have a different transition frequency than the right sides. So if you can flip the atoms selectively of one side into a different magnetic hyperfine state and then image it separately. And you can also choose to flip one of them and blow them out so that you can create this charge density wave state. And the system can be described by this Bose Hubbard Hamiltonian. And these Hubbard parameters are all tunable in the experiment just by rising and lowering the lattice depth. Now, of course, when preparing the initial state, you want your filling rate to be as high as possible so that you can have very long chance as you do the simulation. So that requires the initial temperature to be as low as possible. And this is achieved by doing what we call this staggered emergent cooling in the superlattice, which is by going to this staggered potential. And this results in a very different chemical potential between left and right sides. So you can have the chemical potential which is much lower than the right sides, such that when you go through this multi-insulator superfluid phase transition, you will result in such that the right sides or the even sides are all superfluid, while the odd sides are multi-insulator. And the multi-insulator phase is gapped. So if you create a excitation in the multi-insulator phase, it will cost you energy U. However, if you are in the superfluid phase, you can fill in as much particle as possible. So you can fill in as much excitation as possible. So now as you bring two of them into close contact, the initial entropy in your system will just be absorbed into this superfluid phase. And then later we do this site selective addressing. We can just take out all the superfluid part of the system. And this will give us a very cold multi-insulator phase, which is almost 99% filling in the system. Now, this is a real picture of the experimental system. Well, it's a little bit more complicated than the cartoon picture, of course. So the problem that we are interested in is this QED Hamiltonian. And by discretization, we can construct this one-dimensional lattice gauge theory. And you have this kinetic part, which describes the interplay between matter and gauge field. So the dynamical gauge field operator will couple the fermionic matter fields. And there's this rest mass part, which is the matter fields, and the electric field part, which is the gauge field. Now, this dynamical gauge field operator is constructed from the electromagnetic four vectors, and so as the electric field. So they follow this commutation relationship. And in fact, you can relate this to a spin physics. So if you expand the Hamiltonian eigenstate of the electric field, then the dynamical gauge field is in fact the rising operator of the electric field. So that means if you go to infinite spin, then this will give you the full lattice gauge theory. But if we truncate the amount of spin that you can go to, then this will give you the quantum link model formalism of the gauge theory. Now, however, in our experiments, we need to truncate this to the extreme. So it will be spin 1/2 quantum link model. And the most important feature of a gauge theory is U1 gauge symmetry, which tells you that your system is invariant under the following gauge transformation. And every point in space and time, you must follow the following equation. And if you substitute this into your Hamiltonian, you can get this constraint on your physical state that is allowed in your system. So that means, well, this is just electric flux and charge density. So this is the Gauss's law. And it tells you that the electric field must start at a positive charge and ends with a negative one. So for example, if you have this process, it will be allowed by the Gauss's law. However, if you have an electron move to the right and a single position bumps out, then this will not be allowed. Now, well, we need to implement this into the Bose Hubbard model, and this is by using this staggered potential, and we use this alternating representation. So this will be matter size, and in between the matter size will be our gauge links. And by doing a few transformation, we use a single boson on the matter side to represent a particle or an antiparticle in the system. And the gauge links will be just spin 1/2. So we use a doublon to represent either the electric field to the right or to the left. So, however, the generic full Bose Hubbard model is of course not gauge invariant. So we need to first prepare a gauge invariant initial state. And this is by doing this side-dependent addressing, which is just blow out all the atoms on the right sides on the gauge field. Because if we use this as a gauge link, then a single atom on the gauge link have no representation in our mapping. And if we take it out, well, this actually gives you this fully filled matter size, which is gauge invariant initial state. And however, if you let your atoms to tunnel freely in your system, this is still not gauge invariant because you will also create single particles on your gauge sides. Now, this can be solved by just tuning to this staggered potential. And at this moment, you get this correlated tunneling, a second order process where when your staggered potential match half the interaction strength, you can annihilate two particles on the matter side and create a doublon on the gauge side. Well, and if you do the second order perturbation theory, you can calculate this coupling strength, which is directly related to the coupling strength in the gauge theory. And this actually have direct correspondence in the gauge theory, which is this annihilation of a particle and antiparticle pair and the flip of the spin in between. And of course, in the experiment, we can directly scan this two-dimensional parameter space, and we can find these resonance conditions force on this line, which is U/2 perfectly well. And of course, the system is not ideal, so there might be gauge violations still happening, which is by this single atom tunneling. However, the convenient part about this staggered potential is that it puts an entry penalty on the single particle tunneling. So that means as we ramp up the staggered potential, what you can see is the occupations on the gauge side just dramatically dropped. And the only thing that's creating particles on the gauge side will be this second order dynamics. So do we really have a gauge theory? Well, we need to characterize if the system actually oscillates at the frequency of the gauge theory. And that can be done by just doing this many-mode oscillation and look at the frequency of the oscillation strength. And what we can see here is as you tune up the interaction strength and correspondingly you will tune up the staggered potential, the frequency of our experiment will just approach this gauge theory frequency. And at this large U limit, you can see that these two oscillations are just identical with the gauge theory. So we would also want to just directly probe how many gauge variations are there in our system. And this is by performing this parity projection, which is shining a photoassociation laser onto the system. And that means you can create this unstable molecular state. And this state will rapidly decay and emit a photon. And that photon will kick two atoms out of the trap. So if you have two particles created on the gauge sides, then this will be taken out by this photoassociation laser. However, if you have gauge violation process, which is a single atom tunnel to the gauge side, then this atom will remain there because it doesn't respond to this laser. So this way we can just count how many atoms are there on the gauge sides. And then this is what we see as we ramp up the interaction strength. You can see a continuous decrease of the gauge violation. And through these large interacting limits, the gauge violation becomes just negligible. Now let's look at a few examples in the evolution. So for example, you can have these two pairs of particles annihilate and create doublons, and a flip of the spin in between. So this will still satisfy the Gauss's law. Or you can have a pair creation process, and then you get this pair annihilated. And something interesting happens here is, this is by doing this, you get this particle move from the center to the right. So in fact, you have just local couplings, but we have many body dynamics in our system. And we can do a few other examples, for example. And so quantum mechanics tells you that if you do the measurement, this will be just the sum of all these probabilities, and the system just undergoes this many-body oscillation, and we find it relaxed to a certain steady state. But is this steady state thermal? Well, we need to first define what do we mean by thermal equilibrium. So if you quench your initial state with a certain Hamiltonian, so either the gauge theory Hamiltonian or the Bose Hubbard Hamiltonian, you will get a corresponding energy density, which is a conserved quantity, because this quantum dynamics will conserve quantum energy during this process. And so for this conserved energy, one can solve for the corresponding temperature in the canonical ensemble, or you can use microcanonical or grand canonical as you want. And if we calculate that, we can look at late time dynamics and see if our system going to late times, does the quantum expectation value of the observable would approach the thermal ensemble average. And if it does, we would say our system approach thermal equilibrium. Now let's look at one of the examples. So we first try to quench our system to a finite mass such that it doesn't go to 0.5, which the full Bose Hubbard model would also go to. And indeed, in the gauge theory limits, what you see is this plateau value goes to the thermal prediction. And if you quench a Hamiltonian with this, in the non-gauge limits in the full Bose Hubbard model, what you see is the system would relax to the Bose Hubbard full thermal equilibrium. Now, the second thing we want to investigate is, does the system really forgets? So an ensemble average is, the thermal equilibrium is solely characterized by the conserved quantities, in our case, just the energy. So if we prepare two initial states with the same energy density, then in principle, they should approach the same thermal equilibrium. And that means you should forget all about who they are and where they came from. And at late times, you will not be able to distinguish them. So we need to prepare a set of gauge-invariant initial state with various energy densities. And we can do that by starting ramping the system from this fully filled matter size, which is a ground state of the mass negative infinity Hamiltonian. And as we ramp up the mass from this minus infinity to positive infinity, the system will energetically favor no matter field in the system. So as we can see during this adiabatic ramp, the expectation value of the matter particle density just goes from 1 to 0. And that means you can create this whole set of initial states. They are all gauge invariant, and they will have different energy densities respecting to quench Hamiltonian. So we can identify, for example, here, two states with the same energy density. And now if we quench it, of course, we can choose a different Hamiltonian, and they will correspond to two different initial states. And we can calculate with this energy density, what's the thermal ensemble prediction. And indeed, when you look at it, you take these two very different states from this one, the other is close to 0. And after just a few oscillations, you see that they go to the same plateau value and lost all the information about the initial state. And for the second case, we also see a very similar behavior. So this shows us that this effective irreversible behavior could emerge out of quantum dynamics. And even if you have a closed quantum system through unitary evolution, which in principle admits no loss of information, and yet the system would develop a thermodynamic description at late times. So this is time reversible quantum evolution, and eventually it gives you irreversible scrambling of the initial state information. And indeed, this is very common in most of the systems. So for example, this is maybe not very precise analogy. If you pour milk into coffee, a few minutes later, you get this homogeneous milk coffee. But it will be very strange if the inverse is to happen. So can we avoid this thermalization behavior? Well, for some quantum systems, one can deter the onset of thermalization, for example, by being many-body localized and in the presence of disorder. And this is what you do as they do in the Harvard group and also in Munich. This one-dimensional system, the two-dimensional system. If you ramp up your disorder in the system, you'll see that the imbalance will just persist and to certain times, and you can retain certain amount of initial state information. But a more interesting process would be what we call these quantum many-body scars, which is, well, first observed in the Heidelberg atom arrays, where they have a ergodic system. However, surprisingly, they found that the quantum dynamic is much more robust than they expected. And it was later discovered that this initial state they prepared have anomalously very high overlap with these non-thermal eigenstates, which have very low entropy, as you can see here. So the dynamics effectively trap the system in this scarred subspace, and one would find much slower relaxation rates. So this is in analogy with this single body scarring, where you will find certain eigenstates that have stable trajectories. Otherwise, the random states will just be chaotic motion in the system, like the upper graph. So this is indeed very strange. It will be like your cup of coffee just oscillates between milk and coffee and back again. So, but now the system that can realize this is still very few. And well, it takes the genius of our theory collaborators to extend this phenomenon to the Bose Hubbard system. And the model that we want to study is this PXP Hamiltonian, which tells you that you can only excite excitation, so do a spin flip, if you have on the right, on the left, your all neighbors are just no excitations. So if we, in the Hubbard system, if we tune the chemical potential such that you get these linear tilts with the linear tilt matches the interaction strength, you create this, well, you actually split your spectrum into all these bands, and each of them will conserve this U plus delta energy. So a subsector of the PXP space will emerge out of the four Bose Hubbard Hilbert space, and this one, if you prepare your state here, is going to oscillate between these two ends of your subspace. And now we can map this Bose Hubbard model to the PXP model by mapping this 2-0 configuration to the one excitation. And if the system just oscillates between this 2-0 and 1-1 configuration, this will be equivalent of a spin flip in your system. So we can look at the examples of the evolution. So for example, we prepare our system in this 2-0, 2-0, 2-0 charge density wave initial state. And this will be like on one end of the subspace. Now this will be resonant process to take this 2-0 to 1-1. So you will see this tunneling, and then you can find the system just goes to the center, which is the polarized state. As you can see here, the amount of excitations just goes to the minimum value, and you see this magnetization goes from 1 to almost 0. Now, as you can take this unit cell and move it to its neighbor, well, then this two will also be in resonance. So that means we can have this 1-1 tunnel to 0 again. Well, that means you go from the center to the right, and you go from the near configuration to the anti-near configuration. So, well, it reaches the other end, there's nowhere else to go, so to just go back. Well, of course, this is not exactly happens in the quantum system, but it gives you the idea. Now the system reaches, we'll find it like very hard to equilibrate, and indeed we can see is we can take this to 150 milliseconds, and only at late times you see the system start to equilibrate. So this is quite positional oscillation, and one can also try to stabilize this oscillation by using this periodic modulation of the chemical potential in PXP model. And this was first done in the looking experiment in the Hubbard Heidelberg group. So they find is as they drive the system, you can find the system just the relaxation rate will be much longer. And in our case, we modulate this detuning by modulating the interaction strength, and see this lap time just gets a factor of 4 enhancement. Actually, this is well beyond the experimental accessible time, so we can take this to 250 milliseconds when we can still see the oscillations persisting. So this is effectively just refocusing your trajectory and your many-body wave function and prevent it from leaking into the full Hilbert space, or it's localized in this scarred subspace. So this is quite remarkable because you have this 50-side quantum simulator, and the Hilbert space is like 10 to the 28th, and yet it behaves like a 2-level system. Now, a key feature of this scarred system is that it has slowed growth of entanglement entropy. So for a system, if you is trapped in this scarred subspace, then you should see this linear growth of the entanglement entropy. However, if you have a thermalizing system, then the entanglement entropy just jumps up fast, and at late times you see this volume law dependence with the system size. And of course, if you can drive the system and really traps it in this scarred subspace, it's very likely that we will see the entanglement entropy will be just stagnant. So this will actually tell you if your system is actually localized in this subspace. But to probe this entanglement entropy in such a huge Hilbert space is very difficult. If you want to do quantum state tomography in this 10 to the 28th Hilbert space, it's just impossible. However, this is made possible by doing this quantum interference. Well, the idea is you're doing this 50-50 beam splitter operation. Well, if you have two identical bosons coming into the interference, then what you get at the outcome is the even parity. However, if you have two different Fock state coming in, then what you get out you will get 50% of the chance to have odd parity, and this just directly gives you the state overlap between these quantum states. And now, if you prepare the two systems in the same initial state for the interference, then you just get the purity of the state. And this can be just extended to the many-body system by taking this product of all the interference in the subsystems. And this is done in this Granite group, and they have this single-sided resolution, so they can count the parity of each side, and they take the product of it, so you can actually measure arbitrary purity or the second-order Rayleigh entropy in arbitrary side subsystems. And if you go to the full system, you will just see that it's effectively 0. So yeah, in our case, we will also be doing this interference just evolving the system in one direction with a scar dynamics or non-scarring dynamics, and then we interfere in the other direction with our superlattice double wells. And then, however, in our case, we don't have the single-sided resolution, so we'll be measuring the entanglement entropy of single-sided subsystems, but averaged over the whole system. And this will be similar to the first case, but they only take one side, but in our case, it's like average over all sides. And we can also extend this to look at other stuff like more general quantum overlaps, for example, this unequal time correlation. And this is by first freezing the evolution of one of the state coming into the interference. And that can be done by first doing a microwave pulse and flip one of the chains to a different magnetic hyperfine state, which will have very different response to the magnetic field. So now if we apply a magnetic field gradient in our system, then what we can see is basically one of the chains will see this very small stagger, not stagger, linear tilt, very small linear tilt, while the other will have this resonance condition. So one can evolve with star dynamics while the other is effectively frozen. So as you can see in the measurements, the red atoms are basically just frozen, and the blue atoms will just evolve in the scar dynamics. And now we can flip those red atoms back to blue. And that means we will have identical bosons again in our system. And then we can interfere these two systems together, and this will just give us the equivalent of quantum overlap or fidelity of the system. Now, again, our system is not, we don't have single-sided resolution, but so what we'll be measuring is this entanglement entropy and the fidelity average over the whole system. But nevertheless, we find this single-sided entropy can well approximate the Hubbard entropy calculated by theory. And this would indicate that our system, in fact, is localized in this scar subsector. And that means the entanglement entropy is not spreading throughout the system. And we can also do this fidelity measurement. And it's an approximation, but it does give you an upper bound for the global fidelity here. Now, here comes something surprising. Well, it was generally believed that this polarized state, or in our case, this unit filling state, which have no excitations, is a ergodic system. And indeed, in the non-detuning case, so if you take out this detuning, and then it is ergodic, you see this entanglement entropy rise up fast, and you see no oscillations at late times. However, as we give it a little bit detuning, something interesting happens. We see quite robust oscillations. Now, and yeah, also the entanglement entropy just goes to a low entropy state. And also, if you look at this fidelity, it indicates that it's going to the initial state. So that means we have something that looks like a scar. And also we can drive the system and enhance these oscillations dramatically. So what is happening? Well, it turns out that as you add some detuning into your system, for the polarized case, you see this scarring state emerge out of the bulk of the spectrum. And they are indeed very low entropy state with equal energy spacing. So they are just like this neo state at zero detuning, these are scar states. So this is in fact unconventional scarring. And in the driven case, we perform this Floquet analysis, and we can identify single Floquet mode that is developed very high overlap with the polarized state. So now if you drive the system with an optimum frequency, we can see this persistent oscillation going well beyond the experimental accessible times. So actually, this provides a much easier access to the scarring dynamics, because this unit filling state is much easier to achieve than the neo state for optical lattice experiments. So to sum up, I have showed you how we can realize a gauge theory and observe its thermalization in our quantum simulator. And on the other hand, how we can delay the onset of thermalization by realizing the scar dynamics in our Bose Hubbard system. And we also discover this unconventional scarring regime where the polarized state also presents positional oscillations in the presence of detuning and periodic driving. And of course, in the future, there are plenty of connections to explore. For example, we can go to higher dimensions because we are a two-dimensional system. In fact, effectively, we can do other experiments in higher dimensions or explore this connection to the secable space fragmentation or disorder-free localization or dynamical quantum phase transition. And also this possibility to do quantum metrology or build quantum memories with a scarred system. So with that, I would like to thank our wonderful collaborators. This is the team in Heidelberg, and Jianwei is the founding father of our experiments in Heidelberg. And the thermalization experiment is done with collaboration with the Burgers and Hauke group. And of course, the scarring experiment is in collaboration with the wonderful team from Zlako's group. And Jad is in the superposition between these two experiments. And with that, I would like to thank you very much for listening, and I would be happy to answer any questions.